All right, this lesson is going to be about some matter terminology like element, compound, mixture, molecule. What's that all about? All right, so first up, we have, the definition of an element. Sometimes you hear this referred to as a pure element because it pretty much means the same thing. What it means if you're talking about an element, you're talking about matter that is made of one type of atom only, okay? This is contrary to what we might refer to as compounds. This is distinctly not a compound, okay? So an element is contrary to a compound because a compound has multiple forms of atoms, multiple different atoms in it. So multiple different kinds of atoms, I should say. Multiple different types or, kinds of atoms in it. Okay? At least that's how I sort of think of it. Whereas a pure element only has one type. So some examples of pure elements might be pure elemental magnesium, which is representative of a metal. What you see in a pure metal like magnesium or calcium or aluminum or any others, and again, remember the periodic table, or maybe you may know this or not. The periodic table, if you sketch it out, is made by and large of metals. Like most of the periodic table, everything basically 90% of the periodic table is all metals. Okay, so a lot of the pure substances we see, pure metals, they exist like this. And what they exist like, as shown in this little picture, are their individual atoms. They're actually ions, technically, in what we might call a lattice structure. So they have a regular arrangement, and they make up this huge lattice structure. They are interesting. Pure metals are interesting because they're distinctly not molecules either. It's incorrect to call them molecules, because molecules are these little covalently bonded discrete units. Okay, and molecules can be compounds or elements. And an example of a molecular pure element is found in red there, and that is something like pure hydrogen. And we might represent them like these little guys that you see here in this sample. Okay, they are little individually bonded pairs of hydrogen atoms, so that's why we represent pure elemental hydrogen as H2, and they're covalently bonded, so technically they are molecules. And there is 7 pure molecular elements that exist in what we call the diatomics. So this is what I refer to as the Brinkelhoff twins: BrInCl, hydrogen, oxygen, and fluorine. So we have all of these pure substances, these pure elements: bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine, that exist as little diatomic molecules when they're in their pure elemental form. We may also come across some inert gases or some noble gases. And an example of that is argon. Okay, argon, if you look down on group 18 on the periodic table on the far right, you got like helium, neon, argon, krypton. Those are the noble gases, or the inert gases. They just exist as individual discrete molecules that float around and have kind of limited interactions with one another. Did I say molecules? I shouldn't have. I should say atoms, because they are distinctly not molecules. Okay, again, there's no covalent bonding happening in them, so they are not molecules either. Okay, they're just individual atoms. But since if you have a sample of it, if they're all the same type of atom in that sample, then we call it an element. All right, let's talk a little bit about compounds. So compounds are essentially bonded units made up of more than one element or more than one type of atom. An example of a compound would be something like NaCl. Okay, NaCl is an ionic compound, and the reason it's an ionic compound, or what that means, is that it's made of ions. So it's made of what I'm representing in the red dot here, Na+, the sodium ion, chemically bonded with chloride ions, Cl-. And when they bond together, they exist in these structures, these sort of giant structures that we call an ionic lattice, okay, with alternating positive and negative ions arranged so that the attractive forces are maximized between the oppositely charged ions, and the repulsive forces are minimized between the like charged ions. So this is also an example of something that is distinctly not a molecule. Okay, this is not molecular because they are not made of little discrete units of NaCl. Okay, you can compare that to something like water. Okay, well, I guess I should use the color blue. Okay, so compare that to something like H2O. H2O is a compound. It does have bonds in it. But for H2O, it is made of 2 hydrogen atoms, which I'll represent like this, and then 1 oxygen atom, which I'll represent like that. And they're bound together in little discrete units, okay? And it is distinctly molecular. And you may remember from the last slide there, what makes it molecular is that it has covalent bonds in it. Okay, so this is a covalent compound. Okay, and covalent compounds exist as molecules. So this is definitely something that does exist as little individual molecules. Okay, there could be billions and billions of them, but molecules nonetheless, and that makes it a compound. Sometimes you also hear these terms thrown around like a pure substance or a mixture, okay? And what's meant by that is illustrated here. So you can have a pure substance. It doesn't necessarily mean that it's like an elemental pure substance, although it could be, like the case of the pure metal shown here. So if you imagine like what's in this box, it's pretty much like it's a pure substance and it's elemental. If you look at kind of the sample being represented here, it's a bunch of like what I showed as water molecules on the previous slide. That's also a pure substance because there's only water in there, okay? So there's only water, right? If you look over here, even though there's more than one element in this ionic lattice, it's like only NaCl, for example, so that's also a pure substance. Whereas if you look at what's down here, this would be a mixture because you see you have one kind of molecule here, and then you have another, looks like some sort of element mixed in amongst it. So because there's more than one type of compound or element mixed together, this would be an example of a mixture. You could then start looking at the physical properties of these mixtures if you really want to go deep. And if the mixtures are not all in the same phase, so if they're all the same state or phase, we call it a homogeneous mixture. And if they are in different phases or states and they're mixed together, we call it a heterogeneous mixture. Okay, so you might say, well, what's that like? Different phases. It's like something where you can have imagine like sand and water. Yes, it's a mixture, but the actual solid sand and the liquid water never really mix. And whereas if you look at something that dissolves in something else, like a spoonful of sugar stirred into water, that's going to be more of a homogeneous mixture because everything's in the same phase. So I'll just record this in here as well. If they're all the same phase, that's called homogeneous. And if they're in different phases, that's heterogeneous. Okie dokie.